Hello, today I'm working with DC to three-phase AC circuits. When I first learned about three-phase power, variable frequency drives were brand new and all the older generations hated them, and they didn't want anything to do with all the new electronics, and variable frequency drives were hardly used, and I was told you need three-phase power to get three-phase power. But now with these circuits you can get three-phase power from batteries. The frequencies and phase rotation you get are controlled by the firing package that controls the transistors or IGBTs, integrated bipolar transistors. In this one I have fixed resistors controlling the firing rate. These circuits are what the railroad is putting into all its rebuilt DC to AC locomotives. In rebuilt DC to AC locomotives they're varying the alternating current frequency to control the speed of the motors. So let's analyze this circuit. Right here you have your battery, and right here you have your switch. When you turn power on, this transistor right here fires, sending electrons flowing this direction through L1. Then when this transistor shuts off, this transistor down here fires, and the electron flow reverses through L1, causing alternating current. Then 120 degrees apart from this transistor right here fires, sending electrons flowing in this direction through L2. There's L2. Then when this transistor turns off, this transistor fires, and the electrons reverse through L2. Then 120 degrees apart from the other two, this transistor fires, sending electrons flowing this way through L3. Then when this transistor shuts off, this transistor fires, and the electron flow reverses in L3. So you have current going like this in L1, then 120 degrees apart you have current going like this in L2, and then 120 degrees apart you have current in L3 going like this. I'm not sure if this circuit's correct or not, but I'm going to try it on my breadboard first. So here's what's going on. I have L1, L2, and L3 coming up to a bank of 3 transformers. There's one transformer here, one transformer here, one transformer here. One end of the transformer is connected in a central connection like this, and the other ends of the transformers go to L1, L2, and L3. But we're going to take it up another notch and go all the way up to 240. What's going on is, this is one of the 3 transformers. This is the low voltage winding in the one transformer, and this is the high voltage. Same thing with these 2 coils. This is the low voltage winding of the one transformer, and this is the high voltage winding. And then you come down here to L3. This is one transformer, low voltage winding, high voltage winding. 12 volts goes into the 3 transformers, and 120 240 comes out. I don't have a neutral on the input like I have on the output. Then on the high voltage winding, this is magnetically connected to the low voltage winding. Here's my high voltage winding. I have neutral right here, and I have L1, I have L2, and I have L3 right there. So L1, L2, and L3 are 120 volts to neutral. If you take any 2 connections out of L1, L2, and L3, you have 240 volts. Yeah, my theory's correct, but I don't know if my circuit's 100% correct. I'm just going to go and try it and see what it does. That's just a circuit I drew up in 5 minutes where I combine a DC to AC inverter, as well as a variable frequency drive circuit. So here's your typical variable frequency drive circuit. I have single-phase AC coming in. If you wanted to have 3-phase coming into it, you would just add another pair of diodes and connect your L3 to the other pair of diodes right in the middle, just like these other ones. So here's your variable frequency drive circuit with single-phase AC coming in. This is basically your full-wave bridge right here. It's just connected up a little bit differently, and right here's your filter. And right here is your integrated gate bipolar transistors, and your firing packages would be connected up to these gates that are on each of these transistors. And it would basically do what I just described in the other circuit. And the firing package that would be connected up to these would basically just vary the frequency to control the speed of the motor. Higher frequency goes faster, lower frequency goes slower, and your motor has to be rated for something like this. If you took a standard 3-phase 60 Hz motor and you ran it up to 200 Hz, it could blow up in your face. If you take a dimmer light switch and you stick it on an AC motor, it's not going to change the speed at all. You need to change the frequency to change the speed in an AC motor. I mean, varying the voltage with a dimmer switch works great for a DC motor, but it's not going to work on an AC motor where you need to change the frequency. Well, thanks for watching. Please subscribe, and I hope you learned something.